Great. Okay, welcome everybody. I'm hoping that you all can hear me well. And this is really wonderful to see many of you at this 2024 Rubin Virtual Data Academy. Today is our first day, and I wanted to just give you a brief introduction to the Academy itself and basically what is it going to be covering over the next 4 days for those of you who are participating in the mornings, and 3 days for the session B, which is in the evening California time. All right, so we're going to introduce the data preview DP 0.2 and DP 0.3. We'll tell you a bit more about what they are all about. Then I also will talk to you about the introduction to Rubin Science Platform. Today we'll be primarily covering how to access and work with catalogs. It's going to be both the portal and the notebook aspect of it. But before I go any further, I just wanted to highlight the organizing committee here. Those are the people who are participating, so maybe everybody can say just a word where they are and what kind of science they're doing. So Jeff, maybe you can start with you.
Actually, sorry, I need to step away just for 1 sec. Come back.
Okay, so maybe you can continue with Gloria, if you're on. Not everybody from the Academy Organizing Committee can make it. Christina.
I'm Christina Williams. I'm at Noir Lab. I am part of the Rubin community science team for 2 years now, and I study high redshift galaxies in the early universe.
Great. Douglas, how about you?
Sorry, I was muted. Hello, okay. I'm Douglas. I'm at Fermilab. I've been involved with Rubin for about 5 years now, in one way or another. My interests are generally large sky surveys. I was involved with the SDSS, the Dark Energy Survey, and now Rubin.
Okay, wonderful. All right, Jeff, are you available or not quite yet?
Yes.
Okay.
I am back.
Okay,
Hi, I'm Jeff Carlin. I've worked on the Rubin project for about 8 years. I have dual roles in the data management team and the community science team. And my science interests are in dwarf galaxies that are satellites of nearby galaxies and the Milky Way.
That's great. Nandini, I see you're on a screen again. Tell us about where are you and what are your scientific interests?
Hello, I'm Nandini Hasra. I'm a grad student at the Gran Sasso Science Institute in Italy. I'm in the Galaxy Science Collaboration where I study distance indicators. And I'm also in TVS where I'm studying kilonova observation strategies.
Sounds great. Vincenzo, I believe you're on.
Hello, everyone. I'm a PhD student in Napoli, in Italy, and I'm interested in time domain astronomy, especially looking for transients like supernovae and also like variability of persistent sources like AGN.
Sounds great. I believe that that's all as far as the organizing committee, who probably will be participating in a subsequent day. So let me leave it at that. Before I go any further and talk about the resources, I wanted to bring up the fact that we have also a users committee that is active now on Rubin Observatory. And this is Rubin users committee is charged to solicit feedback from people like those of you who are, for instance, on the call today. And they are also in charge of recommending any kind of improvements to the Rubin operations. So we're acting a bit as a sort of a group that organizes their meetings and collects the reports from them. And if you have any comments, any suggestions, they have their own website, and they also collect information via the community forum. So the users committee is listed here on the bottom. This is the set of screenshots, whatever pictures of the users committee. So if you have any concerns, if you'd like to bring up anything with them, they are all ears for you. Okay, so those are the basic resources here that we have. I'm going to click through some of them. You have a Slack link where you can sign up for communications in real time. So before I go any further, let me just put the location of those slides into the chat box here. Okay, and I hope I can find it. Actually, Jeff, would you be kind enough to put I cannot really see the chat box, the link to the slides that I'm showing right now. So if people want to work with them.
Yes, I'll do that.
Okay, that would be great. All right, so I'm going to go through some of those steps. All the kickoff information for basically Rubin data preview activity is in this link here for delegate resources, and you will see it in probably just 1 second. You might already have seen it because that's all listed in the Rubin Academy website. So that's the one that you can have a lot of links to a lot of resources. So let me just go back and return to the other resources. So the Rubin Science Platform, it is something that we're going to be working with. It's linked here. So the idea behind today's meeting or behind the full academy is that you can either just listen to the presentations of individual presenters, or what would be preferred, you can actually log in to the data.lsst.cloud, and there you can actually follow through with either picking up the notebooks, or you can actually take the tutorial for the Rubin Science Platform portal aspect and follow through that. As far as being able to pick up the individual tutorials for the notebooks, you can actually follow the link that is in the slides that Jeff presumably put into this the chat window, and it has to do with the fact that you can actually extract the notebooks and follow them in your from your own computer. All right. As far as other resources are concerned, we also have a number of portal tutorials, and we're going to be going through one of them for DP 0.2, and you will see this in a bit. And other resources really have to do with the LSST DC2 simulated sky survey and DC2 data release note. So let me just go back to today's session, and let me just tell you what data previews are all about. As you probably know, Rubin Observatory is going to produce huge amount of data. It will be so large that it would be essentially impossible for you to download the data to your own computer. So the mode of operation of Rubin will be that you'll be working next to the data. Most of you probably already know that you will get an account on Rubin Science Platform, and you'll be working through that rather than download the data into your own computer and work on that. So we're preparing those tools for you, and those will be basically tools on the Rubin Science Platform that is for you to work with Jupyter notebooks. That's for people who want to do stuff that is a bit more advanced because it allows statistical analysis, but also we'll have a much more simple interface, which is known as the portal interface, which basically is a very powerful user interface that allows you to access the data, to display the data, to plot it, and so on and so forth. So again, the two different data previews is something I didn't mention yet, are DP 0.2 and DP 0.3. Those of you who participated in maybe some of the Rubin assemblies already know that, but for those of you who are novices here, DP 0.2 is a data simulation that was prepared by Dark Energy Science Collaboration for their own data challenges. And that was reprocessed by Rubin Science Platforms, and it's available to you via those data previews DP 0.2. And again, DP 0.2 can be accessed both from the portal and through notebooks. DP 0.3 is quite different. It contains no images. Those are just catalogs of solar system objects. It's basically a simulation of 10 years worth of Rubin observations of the solar system, and that contains a variety of solar system objects such as asteroids, trans-Neptunian objects, and so on and so forth. And you will see quite a bit of that in the course of our academy. So before I go any further into the first part of today's agenda, which is listed here, I just wanted to let you know that after 2 presentations, we'll have which will be about DP 0.2. We'll have a short break, and then Jake Kurlander, who's one of the people who was involved in development of the data previous DP 0.3, will give us a presentation of the overview of DP 0.3, and there will be some very specific part having to do with the investigation of ephemeриds for solar system objects. One part of the academy that is important that we would like to emphasize here is that towards the end of the session today, after the break at 10 o'clock, we're going to have some collaborative sessions, so you can get to know your fellow students, and that will be done via some breakout rooms that I will set up as time goes on. So those are given a little bit further down, and we have those project breakouts are here. We're planning to have at least one session here in the main room for the general questions and answers. We'll have one session for new delegates to meet and greet, and then there will be 2 for questions regarding the portal functionality and also the notebook aspect. And then we might add some additional sessions, additional breakout rooms, depending on if there's anybody who would like to do this. At this point, maybe I should stop and wait for questions. You can certainly post the questions in the chat, or you can raise your hand. Just a short stop here if there's anything. If not, before I get on to my presentation of the portal, is there anything else that I might be missing? Jeff or Melissa, maybe you have anything that need to be added?
I just added a link for those who haven't signed up for the Slack space. Feel free to use that for communication during the week. And you can see that there are channels for each day. So there's a Session A Monday channel that you can post questions, comments, have conversations there in the appropriate channels.
Okay, thank you, Jeff. All right, so at this point, I'm going to switch gears and get sort of slowly started in on the Rubin Science platform. So let me stop sharing here, and I will go to a different screen nowadays. I will be now sharing the Rubin Science platform, and I will go through through basically the introduction to this. So let me just start sharing screen again here, and Rubin Science platform again will be data.lsst.cloud, and I'm going to be typing this. All right. So when you come in, let me just start sharing the screen again to make sure that you can actually see what my Rubin Science platform looks like. And this is essentially what you will come up with. This is when you enter the Rubin Science platform, and this is basically entering the portal aspect of it. When you log into Rubin Science platform, you can actually connect, and this is, you can probably see it here. This is what happens when you're this is your landing page of the Rubin Science platform, and notice that this is basically now you're now entering the Rubin Science platform portal. Okay, so now what we're going to do is we're going to work primarily with DP 0.2 catalogs. So this is just an introduction to how to use the Rubin Science platform portal aspect, and let me just show you that I'm going to basically following this tutorial that is the beginner how to get to how to create a bright star's color magnitude diagram. So once you log into this Rubin Science platform, you click onto Portal, and that brings you to the screen that you have seen on my previous image. So you have a choice here to go into DP 0.2 images, DP 0.2 catalogs, or DP 0.3 catalogs. DP 0.3 is, again, as I mentioned, solar system, but here we're going to work with the 300 square degree simulated part of the sky that was simulated for the purpose of learning how to use data, but more importantly, to stress test the pipeline for this. Okay, so once what we're going to do here is I'm going to basically enter all the commands that are in the tutorial into my Rubin Science platform instance that I started up on next screen. So the first thing I need to do is I need to make sure that I have the proper tables that are selected. So first I clicked on a proper tab, DP 0.2 catalogs, and then I have the correct table collection. And I think that you have a number of the tables that are within that, but we are going to work with the very first one, which is DP 0.2 catalogs and object. Okay, so sorry about that. I just go back to my to that screen. Yeah, so here I'm going to just continue by basically selecting a segment of the sky that would be 1 degree in a size and will be at 62 degrees and minus 37 for declination, 62 degrees for right ascension and minus 37 for declination. So let me go ahead and enter this to here. This will be in degrees. So I will want to have 1 degree here, as I said. Okay, and 62 minus 37. Okay, so now I'm going to click on the different output column selections and constraints. So on the left-hand side, I'm basically selecting the constraints, and on the right-hand side, there will be an output set of selection, but also the constraints that I'm going to be using. So obviously, I need to use the right ascension and declination, and then there will be a number of additional columns that I will want to extract, and those will be very specifically those 2 coordinate columns, but also the G, R, and I calibrated fluxes. And also we want to make sure that the objects, since we're interested in studying stars, that they're not extended. So extendedness has to be set up as equal to 0. And then we want to have this detect as primary just for objects that are blended. But that's so are there any questions maybe at this point for the people who are trying to follow this? Do I see anything in the chat? And I don't think so. No. Okay, good. So sounds like everything is working fine. So let me just continue here. I'm going to do select for G calib flux, which is the first one of G and I and R, and you can see this here, and I want to have this as an output, and I want to have relatively bright stars, so I'm going to ask for objects that are brighter than 360 nanojanskis. I'm going to do the same thing with the I flux, I calib flux here. Okay, and this is right here. Greater than, so. And same story with an R flux. And again, I will want to do color magnitude diagram and will be in magnitudes, so I will have to convert those fluxes into magnitudes. And you will see in a second how I'm going to do this. So again, I want to have my R calib flux to be greater than 360 nanojanskis. And for the time being, I'm just, will only work with R extendedness to be equal to 0. So the source is not extended. And at this point, I'm going to just move this screen a little bit higher up, and I'm going to, just as you probably have seen it in my tutorial here, I'm going to ask for only about 10,000 objects, so it's not going to take a huge amount of time. The default would be 50,000, and now I can perform my search, okay? You click on the search button. Hopefully you can follow this, and you will see a bit of a funny looking segment of the sky, and it has to do with the fact that I asked for only 10,000 objects in my return. Sorry, I think I made one mistake, so I have to go back, and I have to put this equal to 0, and our colored flags here is 369 nanojansky is good, but I have to make sure that I also asked for those particular flags to be returned to me as well. So I have to mark the column on the left-hand side with the my. Okay, and here we have I-colored flags. Okay, and G-colored flags as well. Okay, so again, please bear with me. Okay, I have all those. I asked for area and deck, and now I can re-enter the search. All right, so you can already see that this interface here is pretty powerful. It now gives you the display of the just go back to this one. It will give you a display of where the sources are, the first 10,000 sources, but also will give you the respective fluxes of the stars that are brighter. Presumably, they're all not extended stars that are brighter than 360 nanojansky. So this is now working. I'm a bit surprised that it's so slow, but it's very likely that many people who are attending the academy, I see 78 people online. Many of you are attending the academy, and therefore you probably are. That's one of the reasons why the platform is a bit on the slow side. But let me just tell you what we'll be doing next. So once that gets returned, we are going to actually display it, and I will be showing you how to do different displays here. It's a little slower than I expected. Sorry about that. All good. Okay. So now we have a large number of sources, 10,000 sources here, and notice that we have three types of fluxes here. So at this point, I'm going to follow the next step, and just instead of having this relatively uninteresting display, I should mention that Rubin Science Platform portal aspect will always display on the left-hand side as a starting point, the coverage of the sky. On the right-hand side will be basically the active chart is the first two columns against each other. So the default of the portal will be the plot of the declination as a function of right ascension. Not terribly interesting. So what I'm going to do now is since I'm interested in plotting the color magnitude diagram, well, first of all, let me just make life a little bit easier for myself. Okay, good. So we have, instead of having the display here of where the sources are, we can actually manipulate the display. You can see the little hamburger icon on an upper left-hand side, and here you can go to results layout. And instead of, if you click on this double arrow here, we can have tables on the left-hand side and coverage on the right-hand side. So notice that what I did now is I've basically modified my display, and now my active chart has array and deck and a table. But this is fine. I just wanted to have a little bit better display here. So now if I want to plot, for instance, let me very quickly plot fluxes against each other, okay? Just so you can see how to display, for instance, G-calibrated flux versus I-calibrated flux can be plotted like this, okay? So this is maybe not all that interesting. You're probably not very surprised that they're all roughly in the same line. Of course, you can turn this into log displays, and the log plot will be done this way. And now you can see that you can actually start displaying things. But I promise that we'll be displaying color magnitude diagram, so I have to do a bit more to this. So now I'm going to sorry about that. I should not be in static, but I should be here. I don't know what happened here. And I should be in tutorials examples. And I should be again in Portal beginner. All right. So now what I'm going to do is I'm going to display the magnitudes rather than colors, rather than fluxes, okay? And in order to do this, I'm going to go back to the Rubin Science platform, and here I'll actually put different values. Instead of the calibrated fluxes, I'm just going to put basically correct value. For X, I'm going to be putting this, which is basically the difference between the two magnitudes. Okay, so I'm going to copy this and paste it into here. Okay. And for Y, I need to use the standard conversion from flux to magnitude. Okay, this is, you probably have seen this conversion here, and there's it's a standard conversion from the from even Wikipedia that was actually listed in the tutorial. All right, so now okay, I can already apply this, and of course this is not particularly interesting because or not particularly relevant because the plot is with magnitudes being greater going upwards. So now I can actually reverse the Y, and now you will have a color magnitude diagram that looks a bit more sensible. I'm not going to spend time labeling the axis. If you want to make it more beautiful, you can label the chart by basically putting the title for the chart as I have it here in the tutorial. But what I want to do is now what I plotted is every single individual measurement, every one of the 10,000 watts. However, what's more interesting, what would be more illuminating, more revealing, would be to plot this in form of some kind of a histogram. So I'm going to do just that, and I'm going to convert this by basically adding one additional plot. So again, this is, I'm going through this tutorial in such a way that you can actually see the individual steps and also learn a bit about how the portal aspect looks like. So I'm going to add a chart here, and my new chart will not be scattered diagram, but will be what I call a heat map. And again, in the heat map, which is basically a two-dimensional histogram, I'm going to also put the very same X and Y as I did before, okay? Sorry about that. X and Y as I did before, so I'm going to pick those up from my tutorial and paste them into the other window. But you can already see that this is a very powerful set of tools. So for X, I'm going to do again the same line that I had here. And again, we have to make sure that you pay attention to all the parentheses and all that. So again, for X, we have this. Missing some parentheses here. This is actually sort of interesting to notice that what you see, yeah, that's better. What you see is that the box, the font turns into red color if something is not correct. So there's nothing in Y, so I need to pick up from Y, again, the same value that I did in the past here, okay? And I'm going to paste it in this box, okay? And color scale, we can make something a little more attractive. Again, how about yellow, orange, red? That's one of my favorite ones. And I'm going to basically ask for 100 bins in the color magnitude diagram. Okay, I'm not going to bother with the titles. You can do that on your own. And notice again, I made the same mistake as before. I did not reverse the y-axis. So let me, for chart options, let me go back, reverse the y-axis. The x-axis should stay the way it is. And again, notice, great. Now you have color magnitude diagram. And this is now let me just close this one because we don't need it anymore. Now you can see that, of course, this is color magnitude diagram where we're plotting apparent magnitudes, so rather than absolute magnitudes, so it does not look like HR diagram. Again, you have a color on the bottom and apparent magnitude on y-axis, and you can stretch the table a little bit, going left, right. Okay, one thing that I wanted to show you after all this, we have this really nice color magnitude diagram that looks a little different than the one that we had here. Again, this is using this with the heat map. You can do exactly the same thing, but instead of using the user interface, you can use astrophysical data query language. It turns out that the portal aspect of the Rubin Science platform is incredibly powerful because it allows you to enter ADQL commands. So let me just copy this guy, and now I'm going to go back to my screen here. And so now I'm going to go into the DP 0.2 catalogs again. Okay, I'm returning to this box, and notice that there is this two boxes on top. One of them says user interface assisted, which is what we've done so far, but it can also go to astrophysical data query language. And the query language is right here. And now I'm going to paste my ADQL command. And okay, great. So now I can do exactly the same thing that I did before, but doing slightly differently. I'm basically using this ADQL box. Okay, so let me click on search. And notice that again, I have this time in my active chart, basically on the right-hand side, I have coverage. Notice that the format of the display is the same as we had before, as we asked to have by clicking on the little hamburger icon. But again, this time I have a display of coverage of positions of individual stars. So let me go to active chart. And this is again the array versus deck here. We don't want that. So you can actually perform exactly the same manipulation. And you can, instead of having coordinates array versus coordinates deck, you can actually pick up exactly the same set of X and Y parameters as before. So let me just do this. I still have maybe another minute or two before I give my podium here to Douglas, who is going to be next one. And I'm just scrolling through to pick up the proper value, proper box for X. Okay. So I'm copying from here, pasting into here. And again, I probably missed the first parenthesis here. Now, I guess I picked up unnecessary words here, I think. I think that's correct. Good. So it's my cut and paste ability not showing as being very perfect here. And then I'm going to pick up this one, hopefully a bit more carefully. And let me do exactly the same thing I did before. And again, I must have made a mistake here picking it up. And that is correct. Now we're doing fine, and trace options, we're going to do maybe now I'm going to make sure that I reverse the Y, and voila, I'm going to apply this, and oh, that's interesting. Cannot display request data. That's interesting. So let me go back here.
I think the underscore deck got stuck at the end when you pasted in the equation in the Y for the Y-axis.
Okay, thank you, Jeff. That's probably all I need to do is to so this
I think it was in the Y.
Okay, good. Thank you very much for keeping me honest here. And you're absolutely right. That should be correct. Yeah, good. And of course, thank you. Of course, I did not reverse the Y. And again, I could perform the same trick that I did last time. Notice that we have a little bit more data here. And that probably has to do with the fact that I did not set up the constraint on total number of return sources. And I could just continue manipulating this image and stuff like this, but I don't really want to take time on doing that because you can, of course, beautify the image yourself. But something that I should point out is the fact that you can actually take this ADQL query and you can actually convert it into a URL. And that is something that is actually at the very end of this tutorial. And I will not go through this, but just so you know that if you have a very complex query, in some cases you want to save it in form of URL, and this is the way to do this. Again, you can go into a little I circle here, and then right here, and then you can save it into URL. Okay, so I just wanted to point this out that this is just basically a full introduction to the portal, but there's a lot more in terms of its capabilities, and I'm not going to at this point elaborate on that, but you will see a lot of that during the course of the Academy over the next few days. This is just an introduction, so you know that you can have actually first sort of easy access to the data using the portal, and then using the notebook will allow you for more sophisticated set of analysis. In fact, you will see the very similar set of analysis to what I showed in using the portal aspect in the next presentation by Douglas Tucker, who is going to do very similar set of presentations, but he will do it using the Jupyter Notebook aspect. So at this point, I'm coming up at the end of my time. So let me stop sharing, and this is a very good opportunity for you to ask questions. You can do it either via via notebook. So I see that. Thank you, Jennifer, for suggesting that I'm going maybe a bit faster than I should. So what was the name of the parameter to click on to exclude the extended sources? Okay, that's if you go back to the screen in my DP 0.2 catalogs in user assisted interface, the extendedness in the tutorial. You probably can't see my screen, but I'm going to share it in just 1 second. But here are the parameters that are already set up. And I think it's what I did is, okay, good. This is where I want to show. And yeah, so it's for extendedness parameters, the extendedness parameters actually are in all 3 bands. I just figured that you don't necessarily have to enter it in all 3 of them. And the way it looks now is, you can take a look on it here on my screen. So did it answer your question, Melissa?
Yes, and Jeff had already answered it in the chat. Thank you.
Oh, great. Okay. All right. So at this point, let me stop. And I think we're gonna transfer to Douglas. I think that we have probably all the questions. Yeah, thank you, Jeff, for answering the question in the chat. All right, so that's for the portal aspect. So Douglas, it's your turn.
Okay. Okay, thank you, Jeff. I'm sorry. Focus on Jeff. Thank you, Greg. Let me share a screen here. And let's see, let me grab the right screen. And I'll open up my chat also in case there's an issue. All right, so if people go back to the Rubin Science Platform startup page, the IDF, the interim data facility startup page here at data.lsc.cloud. So Greg just showed us how to create a color magnitude diagram using the portal. I'm going to show you how to do this, basically the same thing using a Jupyter notebook. And also we aren't really discussing it as part of the main program here, but there's also other ways of accessing and doing similar stuff through APIs, including for those who are say with the TopCat program that a lot of people often use. And if people are interested, we could do something like that. We could have a little tutorial on that during a breakout session. But here, I also want to kind of start out here at this page, and just to let people know if people are having any problems logging in, please send a message to the chat or the Slack message, and we have several people here who can help you if you are having problems logging in. So actually, I started out where I'm not even logged in, so I'll log in. And for me, lab, log in. And okay, I'll see it has my name there. And I'll click on notebooks. And here you have different server options. Generally, unless the notebook says otherwise, you want to log into the recommended. And typically medium is fine. Medium size server is fine. And click on start, and it'll take a couple seconds to start up. Well, several seconds to start up. Okay. And you kind of twiddle your thumbs and think about the things you're going to do. All right, here we are. Okay. Okay, so I have a messy, here's the format. We have here we have a list of things in your home directory, in your home folder, and and mine's a mess. Yours will probably, if you're a newcomer, you'll probably just have a couple things, including tutorial notebooks. We also have all these launchers here. One thing that I find useful for having a terminal window is to open up a terminal window here. And you see you have basically it's like a Unix environment, and you can, maybe I'll make this a little bit larger so people can see better. So you have your home area. You'll notice you have a tutorial notebooks area. And I have a bunch of, let's see, this is correct. This is okay. Okay, so here we have different tutorial notebooks. Actually, oh wait, that is, sorry, this is kind of a bad thing on my part. You want to go to notebooks and tutorial notebooks, and we will be looking, and you double click on these things, sorry. You double click, and we'll be going over the DP 0.2 first notebook, the introduction to DP 0.2. We also thanks to one of our team members, now have a also a version in Spanish. I won't be going through that, but it is there for at least for this initial one. But you'll want to double click on this, and this will open up your notebook. Oh yeah, thank you, Jennifer, for in the comments. Yeah, sorry, my directing structure is a mess here. But yeah, you should be in notebooks and tutorial notebooks. And okay, any problems so far? Everyone's on this point. Okay, so we're basically gonna do a similar thing as Greg did in the earlier tutorial. We will be basically looking at using Python code in a Jupyter notebook to use what's called a virtual observatory service called the TAP service, and we'll use this to retrieve calc data from the co-added data from the simulated data set of that we have for DP 0.2. And just to remind people, the DP 0.2 dataset is a reprocessing of what the Dark Energy Science Collaboration created for their Data Challenge 2. And it is a 300 square degree, it's a simulated 300 square degree area of sky that goes down to about, that covers up to about year 6 of the LSST survey. In the wide field, the wide field survey, and it has 6 filter bands: U, G, R, I, Z, and Y. But so we'll be creating that data set, and we'll be using various packages to retrieve data. We'll also use the TAP search, and we'll also use an in-house creation called the Butler to retrieve and display a deep coad image. So okay, we're looking at a Jupyter notebook. This is a notebook here, Jupyter notebook here, and this is fairly basic. This is a very basic introduction. I know many of you are very familiar with the Jupyter notebooks, but not everyone is very familiar. And I first learned about them about just a few years ago, and they're very nice. Very nice way of running data and be able to you can use these to show others, share notebooks with people, and they can see what you've done. And it's a very nice data. It's a very nice way of accessing the data. So we'll be this notebook will demonstrate the basic functionality of the Rubin Science platform installed at this interim data facility at data.lsst.cloud. We'll be using TAP service, as I mentioned, and matplotlib to plot data. That matplotlib is a Python graphical module, and the LST Butler package. So how to use a Jupyter notebook? Okay, so Jupyter notebooks contain a mix of code, output, visualizations, and narrative text. And you can learn a whole lot about them at this at the Jupyter Notebook documents page. And there's many beginner level tutorials and demos available on the web or on YouTube. Just doing a Google search or looking at Stack Overflow, or even if people are using like various versions of ChatGPT, you can even query ChatGPT to get to learn more about Jupyter notebooks. So Jupyter notebook, as we see, is a series of cells, and there's 3 types. There's code cell, which basically is code that you run. There's a markdown, and actually this is an example of markdown. And there's raw, and raw is basically, it doesn't do any special thing. You can't run it. You can't, it's just shows the what you it's a WYSIWYG. What you write is what you get. but it doesn't run anything. Typically, when you're running the code, you want to run the code cells in the notebook in the order that they appear. And then we'll go do a very simple example of the basic hello world. So here you can click on the cell. You'll see it's highlighted here. And to run a cell, you hit Shift Enter or Shift Return, and you'll get the output of the cell underneath the cell. And you can even also get a measurement of how long it took to run. So 3 milliseconds in this case. Here, this is this, like many of what we've been looking at so far, is a markdown cell. And if you just double click on this cell, actually you don't need to do it on this set of words, but anywhere in this cell, you can double click, and this is what a markdown cell looks like. So you have and you can use it to adjust text, make it look nice. It makes use of the RST language for markdown, but also you can also do a certain amount of HTML in these in these cells also. And okay, so you clicked on it. If you click and return on it, it then just then activates it runs the markdown commands, and you see things as such. Oh, and here is actually an example of a raw cell. You can double click on it. It doesn't change because what you see is what you get. You can hit Control Run. It doesn't do anything. It's a raw cell. So it's I find that I rarely use the raw cells, but the markdown and the code cells are the ones I use primarily. But sometimes the raw cells come in useful too. Let's see. Some little tricks here. Okay, we don't want to do this at the moment. But if you want to quickly execute all the cells in a notebook, you can go over here to this kernel menu, and you can tell it to restart kernel. Oh, sorry, not that one. We're going to restart kernel and run all cells. And it'll basically reset the status of the kernel, and it'll just run and clear out all previous outputs and so on, and it'll just run everything top to bottom. But let's not do that at this moment. There's also another place. You can also go to this little thing that looks like this little symbol here that looks like a fast forward symbol. And you click on that, that does the same thing. Okay, what if you run up and it gets stuck on a particular code cell and just kind of in some weird loop, and you just want to do an emergent stop, and you just want to kill that? You can also come here to this kernel cell and I just hit restart kernel. It'll just reset it. It'll just restart the kernel, and it'll clear out that. It'll interrupt that process. Now, it may take a little while to reset. But you can, if you wait a few tens of seconds, it should eventually stop, and then you can go on from there. What is the kernel? The kernel is basically the computational engine for the notebook, and the Rubin Science Platform, the RSP, uses a Python 3 kernel. It can be thought of as a live compiler. It's like running IPython or something. It's very you can run things interactively or non-interactively. Restarting this kernel and clearing all outputs means that all the defined variables or functions are removed from memory, and all codes revert to their unexecuted state. Other things you might want to do. Well, if you want to look at a table of contents of the table, you notice that we have sections and subsections. If you come over to this far left vertical menu, if you click on this thing that looks like dotted three lines, that takes you to the table of contents. And so you can see all the different labeled section headings. And then if you want to go back, you can just go back and click on the little thing that looks like a file folder and you go back here. Oh, what if you know what if you have this running, you forgot you don't remember what version you requested to have when you start the notebook when you start up the RSP, you don't remember which version the science pipelines is running. Was the easiest way. Let me see, can I open up annotate here? Let me open up annotate here. Yeah, just easiest way is just to look down at the bottom of your browser window in this little window down here, and it tells you you're running weekly 2024_16. Okay, let's here. What's that? Another way you can do that is run it. You can run in the command line or in the command line cell. You can run these Unix commands, and it will basically tell you what version of the kernel you're running and the setup. Okay, moving on, package imports. So there's a lot of different packages that we like to that we often use in a Python cell. NumPy is very popular. It's a numerical it's a package for numerical and scientific computing. Matplotlib, as I mentioned, is a way of using is a way of doing plots in Python. Python is a very powerful method of Python module for dealing with tabular data, manipulating tabular data in what are called pandas data frames. AstroPy is a useful package for containing various astronomy tools. And then there's the packages from the LST science pipelines, which are various sub packages. So we have like the LST.RSP package, enables image and catalog access via the TAP service. The LST data analysis framework DAF.Butler package enables imaging and catalog access via the what's called the Butler, which we'll see a little bit later. And the LST.Geom has various functions for image metadata. And the LST.AFW, which I believe is, if I remember correctly, is astronomical framework .display package enables image display, and we'll look at that a little bit later too. So you can so here we do the various imports. These import them these packages at the beginning of the notebook. You can grab information. We'll kind of speed up here. I'm gonna kind of going a little slowly here. I should speed up a little bit here to get into the interesting things. You can here, I won't go into this, but if you comment out some of these things, you can like take a look. You hit dot and tab, and it'll show you the version, what different functions and data are available for a given package. And there's various help functions which we'll skip over here for now, because we're going to jump into actually grabbing data. So here for section 2, we'll look at the catalog data. We'll use the table access protocol service, or TAP service, which is a site that's provided by the International Virtual Observatory Alliance. Or I mean the definition of it is, and it's been implemented by folks in the Rubin data management. So TAP service uses a query language similar to SQL, or structured query language. This is called ADQL, for astronomical data query language. Now, currently we don't have ADQL not all ADQL functionality is supported by the RSP just yet. More, but much of it is, and more will become available as time goes on. So first, we want to start access to the data source. So we'll run this cell service equals get tap service service. Now this is for the DP 0.2, as you'll see in later tutorials. There's another slight variation on this for accessing the DP 0.3 tap service. Okay, exploring. Let's see. Just exploring data catalog tables and columns with tap. I'll just say here we're kind of looking at the DP 0.2 object catalog, which contains sources detected in co-edit images, which are also these are co-edit images are also known as stacked image or combined or deep co-edit images. This is a very useful thing. This link here to the DP 0.2 schema browser. Everything, all the different columns and tables that are available for DP 0.2 are listed here, and it's very useful to take a look there. But we won't. Well, that'll be left for the user to look at. When we query the tap service, there are two different ways for displaying things easily. We can create a AstroPy table using the .toTable function, or we can convert all the way to a pandas data frame using joining the .toTable and toTables functions. We do warn, do not use it, for those who know about this, do not use the toTable.show in notebook method, because this causes things that may cause your notebook to hang. And so yeah, basically don't do that. Here we have three optional exercises. We'll actually look at exercise 1 and 2 very briefly. So you may wish to comment these out. So here we use, tap queries, ADQL queries have at least 2 and perhaps 3 parts to it. There's a select section where you ask what columns you want from a given table. And so we are selecting from the table called tap schema tables. This will show us the metadata for DP 0.2 for the different tables. We will we'll pass this over into the tap service search function, and then we'll convert the results from that search into a pandas data frame, and then it will display that pandas data frame. And once again, to run this, hit Shift Enter or Shift Return. And here we get a variety of tables that are available in the taps in the DP 0 tap service. And actually, interestingly enough, this also can things that we don't want to look at. The DP 0.1, which is deprecated, but there's things like the CCD visit, different imaging for DP 0.2, and we'll be looking at this one, this DP 0.2 DC2 catalogs.object table. And you see more about those in that schema browser link above. And let's also do a quick look at exercise 3. Here we select various columns from the table, from the tap schema columns table, and we're only interested here in the table, in that one table that we're concerned about, the object table for DP 0.2. We'll submit this query to the tap search, and then we'll convert it into a table. Now this is really long, so we're not going to actually list the table. We're just going to print how many results are available, how many columns there are in this table, and we'll find out that there are 991. If you want, and this is left to the user, you may comment out this next line and see all 991 columns. I suggest really going to that schema browser page from above. And we'll skip over this and jump over to retrieving data with TAP. Couple of important things. LSST breaks shards or breaks up data into ARIA, and the database is broken up into ARIA index shards, areas of ARIA index. And it's, if you set a given area sky, it's faster to query that way. You can also request to use the max rec or the select top method to just return a small number of objects. And this will speed up your queries if you can constrain to a small area of the sky, or as opposed to creating the whole database. We also recommend to use the detect is primary function. We saw that in the previous in the portal, and this basically data run to a deep blender, and we save all the parents and children, but we really are interested in just the final results, the children. So saying detect is primary just gives you the final result, not the intermediate measurements. Okay, we saw earlier how to convert from fluxes into AB magnitudes. You can do this here. You can do this in the notebook two ways. You can just query for fluxes and then convert them afterwards using a Python. Or there's also a function that was written to convert the fluxes into magnitudes as part of the query, as part of the ADQL query, that's called. You can use either one of those. It's fine. I won't dwell on those because we're running out of time. But why don't we just let us grab the first 10 objects that are identified within 0.5 degrees radius of roughly the center of the 300 square degree area of data challenge of the data preview 0.2 processing of data challenge 2. So the center coordinates are roughly near RA of 62 and DEC of minus 37 degrees. So we'll set those as the coordinates that we're interested in. Then we can use select. We only want to choose the top 10. We choose the RA and DEC coordinates, the chord RA, chord DEC. We choose. We also want to return the detect is primary flag. We want to grab the R-band calob flux and the R-band C model flux and the R-band extendedness from objects. And then we use this ADQL query that looks for things within in this case 0.01 degrees of R and DEC. And we include the user coordinates in this query, and so you can run this, and you can create it to a table. We aren't displaying it just yet because first we want to convert this into our CAD mag and our C model mag into the fluxes into magnitudes, and we saw how to do that in the portal. And here are the equations, and then you can take a look at the table. And we have the RA, the DEC, the detect is primary flag, the calob flux in Nanojansky's, the RC model flux in also Nanojansky's, the extended parameter 0 or 1, the calob mag and the R calob mag. So these are AB magnitudes, and they're all pretty faint, around 25, 26, 27. Because most things are going to be faint. Okay, I think that's just quickly go through this here. We're going to do a cone search. We're going to impose that the detect primary is true. We're going to only look at fluxes things that are brighter than 360 nanojanskys. That's about 25th magnitude. And we're going to set the extendedness parameter to 0, like we did in the portal tutorial. And we'll just grab the first 10,000 objects. And so we select the top 10,000 objects. We want the RA index. Here we use that other routine to convert the fluxes into magnitudes. And we grab the caloplex. The caloplex is basically a 12 pixel radius circular aperture. It's defined as it's supposed to be used for doing photometric calibration of the sample. And it's also useful for like looking at stars. I will select from the object catalog as before. Here we're looking within 1 degree radius of our chosen coordinates, of the user coordinates that we selected before. Here we ask it to say only return things which detect is primary is 1. We select things which are fairly bright, and we select things which have an extended parameter of 0 in G, R, and I. So they are seen to be point sources in G, R, and I. And then we'll just we'll get we will then send the results to an AstroPy table and print the link to the table. And yep, it had 10,000 back. It took a little over a second. And then we'll take a look. And we see RA depth and the magnitudes. And you can also convert those into pandas data frames, but we will skip over that to quickly jump over to making a color magnitude diagram using matplotlib. So we can use this plot function, and we're plotting R minus I, and versus we're placing G as the y axis and G minus and R minus I as the x-axis. We'll make them circles. So they'll use the little O, and we'll use a marker size of 2 and a transparency of 20%. And we'll label them, and we'll just quickly plot them. And here we get our color magnitude diagram of G versus R minus I. You'll see the red stars are quantized. Those are basically an effect of how the simulations were created. Red stars were simulated with quantized colors. But just simulation. What we hope not to see that in the real data. But yeah, we shouldn't see anything like that in the real data. Okay, let's very quickly, since I'm kind of running out of time, let's look at image data. We'll primarily people look at either single exposure or calyx observation in a single filter, or the co-added data which is of a single filter. So those are CaliXP and deep co-ads. And we'll look at deep co-ads here. So co-ads are are tessellated. The 320 degrees are tessellated into tracks, and then the tracks themselves are tessellated into subregions called patches. And so to find, so we want to grab a point in the RA deck and grab the tract and patch for that co-ed and retrieve that. So we'll create an instance of the butler. So the butler is a means of accessing data without necessarily knowing what file format or where it is in a directory structure. It can be anything. It's a simple means of simply accessing the data. So we'll create a butler. We want to use the DP0 0.2 data set, and we will use what's called the DP0 2.2 I runs DP 0.2 collection, and this will define the butler. And we happen to know someone found a nice nifty DC2 galaxy cluster at a given position, and so we will we'll use that as our RA index, and we will use what's called a sphere point to identify to feed this information into the butler. The butler understands sphere point, or information for the butler knows how to access the sphere points, and we'll use that using a sky map. The sky map is that tessellation function, that map that encodes all that tessellation. So we will get from the butlers the sky map for DC2, and we will find the tract and the patch, and then we'll print out that information. So we'll find out it's in tract 4431 and patch 17. And then to identify, Butler requires a data ID. So for deep coads, we need the filter band, the tract, and the patch. And we'll grab that. And then I'm running out of time, so I'll just very quickly say there's this astronautal framework display method. We'll use matplotlib as the back end, and we will and then we'll just use this function, this AFW display function, to plot using a hyperbolic arc sine scale and z scale. Sort of for those who've used like DS9 in the past, is similar to that, and we'll plot our nice cluster, which we see here. And actually, I'll just kind of conclude there. Sorry, I went a few minutes over time, but I'll leave it there. Are there any questions? And I'm afraid I can't. Oh, let's see. I see in the chat, Armin requested how to go back and switch the kernel. Oh, yes, this is a very useful thing. I hope I remember how to do this. Sometimes you've logged in and you go to and you see, oh wait, this kernel requires some obscure kernel, and I need to restart this, and I don't want to that's going to go all the way to the beginning. So if you go here, if you go to your window, and I don't know, Jeff can remind me, I believe it's you just remove everything out up to ND, so data.lcc.cloud/ND and /home. And I'll put this in the chat if this works. Okay, yes, that was it. So I'll put that in the chat. And then you can stop your server and then restart your server. And this will take a few seconds. Then you launch your server and you say, I want to start one of these, one of these other things, with these previous releases or something. I'm not going to do that. Let's go back to the original one. Then you hit start again. Okay. Are there? Oh, I didn't hit enter. Okay. Are there other questions? And I'm afraid since I'm sharing screen, I don't see people's raised hands, so someone can let me know if there's a raised hand.
I don't see any raised hands, Douglas, so I think that we're okay. And I don't see anything at this point in the chat window either.
All right.
One thing that came up in the Slack channel is was a question about the there's like a Git extension and a NBDiff extension that are installed that you see a little link for at the top of the above your notebook. And
oh, sorry,
I actually have never used those before. So
oh, where is that?
Yeah, that was my initial thought too, is I've never used those because I always use Git from the command line. But when you open a notebook,
oh, okay, let me let's see.
And I'm not sure if it has to be, I suppose it has to be in a Git repo, but we'll see.
Let's see, I can open this generic notebook.
Yeah, see at the top, yeah, there's this Git diff. I've never
I
used
have
it, so I'm glad that Mike asked about it.
I have no idea. Did you find an answer for him?
Not really. That's the first I'd explored it. So it doesn't. Okay, I guess in your case, it's saying there are no changes. So
Let's
since
see. I guess I could go to one of my things I was messing around with. Let's see. Was I doing something here? Ah, interesting.
yeah.
Okay, you learn something new every day.
Yeah, thanks for asking,
Uh,
Mike.
I don't know. Yeah, that's a good point. Okay, thanks. Okay. Let's see. All right. Anything else? Oh, let's see. Let's see. Is it possible to reset all files and data we have already had? My root directory is too crowded. I need to clean system. Oh, that's a good question. I mean, uh, that might be something to ask at one of our breakout sessions. I mean, you can always do cleanup um, using Unix commands. I mean, you do want to be careful. You don't want to blow away important things. And you can see here that I probably should do a lot of cleanup myself. Let's see. But I mean, you can always use like the rm command or move command. Uh, I mean, like, let's see, make dir CSV files and move. I can move all my CSV files in this directory into this new directory, and it starts looking a little bit cleaner. But yeah, you don't want to delete your notebooks directory, and you don't want to delete your work directory. Um, so yeah, but yeah, let's see. Oh, let's see. There's a request. Yeah. Share the link for switching to different pipeline version. Okay. Oh, I see. Sorry, everyone. I sent the link to Armin directly, not to everyone. So there's a link to. I sent the link to the how to change your if you need to change your the kernel version, the pipeline version. All right. Any other questions? All right. Well, if you have other questions, be sure to there's always Slack or the chat, and I will stop sharing here and pass things back to Greg. So thank you.
Right. Thank you very much, Douglas. This is great. We're running a little bit behind time, but I think that everybody probably needs a short break to get their coffee or whatever else. So maybe we can reconvene here at 9:30, and then Jake will take over, and we'll just cut into the collaborative / breakout time. So you can feel free to just go off for 5 minutes if that's okay. And then Jake will take over at that point. Okay, so I'm gonna put the startup screen again, so you know what to expect today. All right. And then I'll be here, Jake, so whenever you're ready, you can, I'll stop sharing screen and you can get on. All right, Jake, I think it's 9:30, so you probably can start if you wish.
Okay. Hello, everyone. I'm Jake Kurlander, and I'm going to be talking about DP 0.3, Data Preview 0.3, the LSST simulated solar system data product. I'm going to be presenting a notebook that gives an overview of the tables, and I'd like to make sure everyone has access to this notebook. So we're going to be running this notebook in the Rubin Science platform, data.lsst.cloud. So if you'd like to follow along and you don't already have a tab that looks like this open, please take a moment and navigate there. And to get the notebook, we're going to be cloning a Git repo. For some folks, this might be something you're very familiar with, but I'd like to walk everyone through it. Just for anyone who hasn't done this before. And there's two places we have a link to this Git repo. The first is in your email. Jeff's logistics email has this link down at the DP 0.3 delegate contributed notebook GitHub link. Though I heard in the Slack that this was going to some people's spam, and similarly, I got a header about that. I trust you, Jeff. Sorry about the untrusted sender message. So this is the GitHub repo. The other place we can find this link is in the slides for today. Slide 8 has that same link right here. There's only some folks on these slides, though I see the number of people looking at this Google Slides is going up rapidly. So perhaps folks are getting to it this way as well. Slide 8, link number 2. And these both send us right here to the Rubin DP0 delegate contributions GitHub repo. Once we're here, we're going to go to code, this bright box, and click on HTTPS. Then we're just going to copy this link. And select the text or click this copy to clipboard button. And now that we've got the link to the GitHub repo, which has the notebook that we would like to run, we're going to come back here to the Rubin Science platform. And if you already have something open, just hit the little plus tab in this tab section. We're going to make a new terminal. Or if you already have a terminal open, you're welcome to use that as well. And from wherever you'd like, but probably your home directory, we're just going to write git clone and then paste that link. So we're going to run this command, which is going to clone that GitHub repo to our home directory. And that should run and take a couple seconds. And we see pop up here on the left side in our file browser, a new folder named Delegate Contributions DP03. This is the repo, contains some notebooks. We're going to be running one called Ephemerides Investigation today. It contains less actual investigation of ephemerides than it did when I started making the notebook. I changed it to mostly be about an overview of the DP 0.3 tables now. All right, so hopefully everyone now has access to this if they'd like to follow along. I see some messages in chat. Oh, perfect. The links are being listed there, so we are all good. And yeah, we have the notebook that we would like to run. So this is an overview of the DP 0.3 tables. We are going to learn about the 4 tables in DP 0.3, about their contents, a little bit about the inputs to the DP 0.3 simulations, and what we should and shouldn't use them for. I've got a bit of insight into this. I worked along with Pedro Bernardinelli and Joachim Moynes and Sam Cornwall, Ari Hines, and several other folks on making these simulations. And so we've got some insider information here. All right, so this is a pretty lightweight notebook. We've only got 3 imports: matplotlib for plotting, pandas. As mentioned in the last session, there's a few different ways we can manipulate these tables, but pandas I find is the most convenient and the most widely known. And finally, a tap service. So from lsst.rubin Science platform, we're going to grab a tap service, and just for anyone newer to Jupyter Notebooks, to run cells, I'm holding Shift and hitting Enter or return, and that's just automatically running these cells as we go, and we can see which cell is highlighted with this blue here on the left. So as alluded to in the last session, we have to use a different tap service for DP 0.3 than for DP 0.2 or 1, the Galaxy and Star and Cosmology simulated data product. Instead of using TAP, we are using SSO TAP, or Solar System Object TAP. This is just the name of the service that's going to get us the simulated solar system datasets. And from the SSO TAP, we're just going to run the query, select table name from tap schema tables. So we're just going to ask for the name of every table, and we're just going to print those names out. And very quickly, we get a list of all these tables. Several of them are metadata, so anything that starts with tap schema or the uws.job table, those we don't care about too much. The real data is all in these 8. And we can see these 8 tables are broken up into 2 groups. There's the 10-year portion. So we've got 4 tables that are for a 10-year data set and 4 tables that are for a 1-year data set. In general, I recommend folks query things out of the 10-year data set. If you're using DP 0.3 to try to build a pipeline or practice building a pipeline that is going to have to run on 10 years worth of data, it's nice to have 10 years of data to play with. If you want to get a sense of what LSST data is going to look like at the end of the 10-year survey, or really anywhere after the first year, the 10-year data set is the one to use. But we're going to be using the 1-year data set for this notebook because it's 1/10 the size, and so the queries return a lot faster. And so it's just going to be nice and quick getting us through. But we see 4 tables here in each of these 10-year and 1-year data sets. We've got dia source, which is the difference image analysis source table. These are all of the 5 sigma detections of a point of light in the sky that was not there in the night before. This is the subtracted images that are going to be produced by the Rubin pipelines before it even gets to the solar system folks to try to identify things. Then we've got MPC orb. This is the Minor Planet Center's orbit catalog. This again is not a Rubin specific data set. But this is our simulation of what MPC orb will look like after the first year of Rubin discoveries. So this contains orbit information and object information about all of the simulated objects and the real objects we simulated, the synthetic and real objects that are simulated for DP 0.3. So this includes orbital information, absolute magnitudes, and orbital uncertainty information, that sort of thing. And then we've got SS objects. This is the and SS source. These are 2 internal tables, and they include the data that the Rubin solar system pipelines will generate for our own analysis of these solar system objects. So an asteroid, a comet, and solar system sources. So the dia sources that have been associated as belonging to a real object. So here's a handy table breaking down the 4 tables into 2 categories in 2 ways. So there's a lot of important information in all of these tables, and these are going to be the tables that Rubin LSST eventually does keep track of all the solar system information in. And things that we care about a given object or a given detection are going to be split up in these tables based on what I'm about to say. So it's important to understand why they're broken up the way they are, so that we can go and find the things we'd like to find in these tables. So there are the per object tables, SS object and MPC orb, and the per detection tables, SS source and dia source. And these are separated from each other based on whether they are generated by the Rubin solar system pipelines. And these tables start with SS, so this is the code that's being run by the telescope every night or every day to discover objects, find objects, and compute information about these detections, or whether this information is inherited from an external source. So let's say that we care about an object's orbit and color and brightness. The orbital information is all going to lie in MPCORB, the Minor Planet Center Orbits catalog, because that's an external service. It's the gold standard for all sorts of information about objects, including orbits, and we end up caring a whole lot about including non-Rubin detections in the orbital fits on every object. And so all of the orbital information ends up in MPCORB, but when we care about an object's colors, Rubin's photometric bands are unique to Rubin. And so since Rubin is the only observatory that's going to be observing in Rubin bands, all of the color information in Rubin bands is an SS object. And so the information we care about is often going to end up being split up between different tables. And towards the end of this notebook, we will work on joining things together and cross-referencing different tables, get the information we need out of multiple things. I see 11 things in chat, so this is a good place to stop and look for comments. Oh, okay, git clone. Looks like everyone's doing all right on git clone. Perfect. Okay, let's look at the contents of each of these tables. So for each of these tables, their names, MPCORB, SS object, DS source, and SS source, we are going to use the SSO tap to search, select everything from TP03 catalogs 1 year, and then that table name. And we're just going to ask for a single row from each table. So this is real quick. And then we print out the columns. So this is just going to give us the columns of every DP03 table. We see in MPCORB a whole bunch of orbital parameters. So we've got eccentricity, inclination, pericenter, longitude of ascending node. This is the stuff we care about for asteroid orbits. We also see some minor planet center specific things that aren't going to be very relevant to Rubin. So like computer, that's the name of the person at the minor planet center who computed the orbit. And then we notice that MPCORB has an arc column. This is the orbital arc, the duration over which this object's orbit is known. We notice that same column name in SS object. Arc is there as well, but these are not the same arc. So just as we said before, the SS object table is for Rubin solar system generated information, while the MPCORB table is for inherited information from the Minor Planet Center. So SS object, its arc is the duration of observations made of that object by Rubin, while MPCORB is the duration of observations of this object made by all observatories that have reported their detections to the Minor Planet Center. So hopefully that gives you a sense of the difference between MPCORB and SS objects as tables, and where to look for the sorts of things that you want. SS object, the vast majority of its columns are dedicated to band-based information. So we see a whole bunch of columns beginning with G, with I, with R, with Y, and U and Y and Z. These are the Rubin bands, and most of SS object is about the colors of these objects and how well we've constrained those colors. Then moving on to the source, the detection-based tables. DS source, this is the inherited one. This contains all of the information about these sources that is generated by the difference image analysis pipelines. This is all the information that is not inherent to this source being a solar system object. So if it was a star, we would still have this information. If it was a galaxy, we would still have this information. So this table includes things like right ascension and declination. It includes things like magnitude and the band in which the image is taken, the time of the observation. Meanwhile, SS source, solar system object source, contains solar system object specific information. So these are things like the ecliptic coordinates of this detection, the object's heliocentric position, velocity, and distance at the time of this observation, the magnitude we predicted this object would have at this time in the solar system object pipeline, and the distance from Earth this asteroid. So SS source is for asteroid specific information about a detection, while DS source is for things that this detection would have even if it weren't a solar system object. We can learn a whole bunch more about all of these columns in the schema browser. We've got a link to that here. It's got documentation and data types and units for every column in every table. It's important to note that this is for DP 0.3, and while we tried to model this as closely as we could after what we expect the Rubin tables to finally be like, those table schemas for Rubin proper or for LSST proper weren't finalized until after DP 0.3. So if you build a pipeline with this information, you may have to change it, at least the column names, before real data starts coming out. And finally, there's more DP 0.3 documentation, including, very importantly, a list of known issues. There are several problems with DP 0.3 that we'll hopefully get into as this talk goes on at dp0-3.lsst.io. In particular, the known issues link and the data products link are real useful. All right. Next, we're going to move on to trying out some example queries for each table and messing around with the data itself. But this is a really good moment to stop and ask for questions. So if anyone's got anything they're confused about, something you'd like me to talk more about when it comes to these tables, the data accessible in these tables, or how to query these tables, please raise your hand or unmute and ask, or ask in chat. Okay, sounds like folks doing all right. So let's move on to an example query for each table. So one interesting sort of a useful orbital parameter, one that's very intuitive and understandable, is an object's pericenter. That's the asteroid's closest approach to the sun. And this is a distance, so how close does it come to the sun? And we represent this in AU, in astronomical units. This is represented by Q, and it takes the place of semi-major axis in our data set. We used cometary coordinates, so we're only really getting pericenter distance in terms of distance from the sun. So just for fun, let's ask the MPC orb table for the 5 closest and the 5 furthest objects by pericenter approach in the 1-year MPC orb table. So we're going to make a service.search. We're going to select a few columns. MPC designation, this is the name of an object. Q, that's the pericenter approach, the distance it comes to the sun in astronomical units. And then little e is eccentricity and inkle is inclination. These are the other 2 most exciting orbital parameters out of the 6. We're going to get this from DP03 catalogs 1-year MPC orb, and we're going to order by Q. So this is saying take that table, sort it by Q, and then just give me 5. By default, it orders from smallest to greatest. So just asking it to order by Q, limit 5 is going to give us the 5 closest, the 5 with smallest Q. And then we're going to make that same command again, but this time descending. And this is going to give us the 5 farthest objects, the objects with highest pericenter. We're going to take the results of these and pandas them. This gives us a pandas data frame, which is my preferred way of manipulating tables in Python. And in just under half a second, the Rubin Science platform returns to us the 5 closest and the 5 farthest objects. Here they are. We have 5 objects with somewhat similar looking MPC designations and very, very small pericenters. We also see that they tend to have very large eccentricity. Eccentricity tends to be between 0 and 1, and pretty solid inclinations. These are in degrees. So these are on pretty chaotic, very tight orbits. Now, the MPC designation here tells us a little bit about these objects. So DP 0.3 is made out of several different. It's made out of the simulation of several different populations of objects. It includes every real object known as of May 2023, when the dataset was created. It also includes the Pan-STARRS synthetic solar system model. And every MPC designation that starts with an S in this in DP 0.3 is a S3M. It's a Pan-STARRS synthetic solar system model object. So Pan-STARRS synthetic solar system model was used for the main belt and the near Earth objects and the TNOs, and to extend the population of objects much deeper to much dimmer objects than than currently exist, since Rubin's going to find objects much dimmer than currently are known. But it has a couple quirks, and one of those quirks is that the near Earth object population extends very close to the sun. And in particular, these pericenter distances at the very closest are inside the sun. These have a closest approach smaller than the sun's radius, so that's a problem for the Pan-STARRS synthetic solar system model. These are sort of unphysical orbits. By comparison, if we look at the farthest objects, these have pericenters out as far as 60, 70, or even 80 AU. So these are getting between 2 and 3 times. They stay at least 2 times farther from the sun than Neptune does at all times. And we see that their designations are quite different. Their designations are in the form of a year and then a space and then 2 letters and a number. These are actual minor planet center designations. These aren't synthetic object IDs. These are actual names of objects. And so the fact that the 5 closest objects to the sun in this data set are all S3M, and the 5 farthest from the sun are all real objects, even though Rubin's going to discover objects very distant from the sun, and it's going to be very good at finding dim and distant large objects, shows us that our TNO model, the model of synthetic objects out past Neptune, probably didn't extend far enough out. So because S3M was made before we knew of objects this distant. So this highlights a couple of the quirks of the synthetic models that we chose. There are a couple unphysical spots, but by and large, the objects are where they should be. The bulk of objects in the main belt are distributed just like the main belt. We have a big trans-Neptunian region, a huge diversity in sorts of orbital classes of objects, but there are some quirks to look out for. Let's also just check how big this table is. So we're going to select count of everything from this 1 year MPC orb. And hopefully in just a couple seconds, we get the size of the table, 14 million. So we have 14 million synthetic objects included here, including all the real ones. About 5 or 4 million of those are expected to actually be discovered by Rubin over the course of the survey. And let's see. Bob asks, would Rubin be able to see the closest objects to the sun? That is a fantastic segue question, Bob, because we are next going to look at the SS source table, and the example query I've decided to show is to find the observations with the highest phase angle. So the phase angle of an observation is the angle between the sun and the Earth from the object's perspective at the time of discovery. So when an observation is taken at opposition, when we're pointing directly away from the sun, an object directly along that line of sight will have a phase angle of 0, and an object directly between the Earth and the sun will have a phase angle of 180. And we see that at the very, very distant end, the very, very high phase end, Rubin is actually going to have several really high phase angle observations. Now, again, this is just a few observations out of tens of millions, but a phase angle of 122 degrees is very high, and so that the twilight survey is doing its job. We are somehow able to swing all the way in and get some observations of asteroids that are well interior to the Earth's orbit. You said circular. It looks to me like these inclinations 0.99. That's incredibly centric. It's almost parabolic. All right, we can come back to these SS source detections later and try to investigate the objects that are creating these detections if we have a bit of time at the end. But since we are running a little low, let's just keep moving. Now let's do a query from SS object. So the sorts of information that SS object has, this is object-based data made by the Rubin Rubin solar system pipelines. And in particular, we see lots of color-based information, lots of band-based information. And so let's select the number of red band detections and the absolute magnitude in the red band. And let's get just the 5 objects with the most detections in red band. And in half a second, this query comes back. We have 5 objects. They have pretty good distribution of absolute magnitudes. There isn't a clear. It's not clear that brighter objects are definitely better detected. These are not particularly large objects in the solar system with absolute magnitudes between 10 and 15. There's objects with negative absolute magnitudes. So 10,000 or 1,000,000 times larger. But these objects have a ton of R-band detections. Remember, this is just the 1-year catalog. This is just a single year of Rubin data. And R-band is just one of a few bands. We've got six bands, and R-band's maybe a third of total solar system bands. So it's sort of crazy that an object is able to get, several objects are able to get well over 100, 130 R-band detections in just this 1 year. Rubin's only expected to cover the sky in the Wide Fast Deep survey about 800 times over 850 times over 10 years. So it's like 85 detections a year across all bands. So how are these objects getting well over 100 detections in just one band and in just 1 year? Well, it's because of the deep drilling fields. So there are some spots in the sky that Rubin's going to return to a huge number of times over the course of the survey. It's going to keep imaging these small, 10-ish degree, 100-ish degree regions of the night sky many times. A serious factor more repeat visits to these locations in the sky than to the average wide fast deep fields. And so we end up with some asteroids that we're going to have an incredible amount of data for. In particular, the slow-moving objects, so the TNOs and the Centaurs that end up in the wide fast deep fields. I think in the 10-year survey across all bands, there's a TNO that gets 12,000 detections in the survey. So this is going to be, we're going to have the best measured light curve of any solar system object by some ridiculous factor. So that's one really amazing thing about Rubin is just how many detections we're going to get. And in particular in the deep drilling fields, there's some really cool stuff that can happen. All right, now we're going to move on to the last table, and we're going to investigate diasource, and in particular, we're gonna learn a trick. So diasource has something like 50 million, I believe, 50 million detections across the 1-year survey, and this is it corresponds to about 500 million, 500 million detections in dia source across the 10-year survey. Let's just get the size of that table, verify what I'm saying. Yeah, 48 million detections over the 1 year. This is actually an undercount. It's we messed up the colors by about 0.2 magnitudes, which should everything appears about 0.2 magnitudes dimmer than it should in DP 0.3. So we should expect something like 30% more. So maybe a billion detections across the whole thing. Sometimes you don't want a billion detections. Sometimes that's going to take way too long. You can't download all that, or you don't want to hold it all in memory. And instead, what you'd like is a uniform sample of a table. Now, it would be really convenient in order to take uniform samples of a table, if there was a randomly generated number in some column. If there was one column that was just a random sample that we could use to draw random samples. And it turns out this is almost true. So there are two ID columns, the SS object ID, the solar system object ID column, and the dia source ID column. These are each 64-bit integers, which are not randomly generated, but hashed. So from a statistical perspective, we can consider them random numbers. And so whenever we would like to draw a random sample from a table, we can use this trick. So let's say we want like 1/4% of the table. We can generate the number that's almost 2 to the 63. So 2 to the 63 times 1 minus that fraction. And because there's positive and minus, we're going to have to double that. It's 64 versus 63, so off by 1. But if we then select some information, so let's say we want the band and the magnitude of every solar system object dia source in the first year of Rubin, where the dia source ID is greater than this, that's going to give us a random sample of about this fraction of all of the dia sources in Rubin. So instead of having to download all 50 million, we're just going to have small, uniformly distributed fraction, and perfect. We see we got, what is that? 120,000, 121,000. If we divide that by fraction of table, we find that, yep, got an expected value of 48 million. That's exactly what we saw just a moment ago. So we did a good job. We took a random sample, and now we have a whole bunch of detections by band and magnitude that we can plot. So here's a histogram of the magnitudes in each band, and we see right away that the I band and the R band are the real workhorses of Rubin solar system discoveries. They have by far the most detections and are generating a huge fraction of the discoveries, but also the G and Z bands are pretty big contributors. So most bands of Rubin are really useful for solar system science. It's U and Y that are less useful, and we actually forgot to generate the Y band. So, excuse me, forgot to generate the U band. So Y is the only fair one in here. And I'm seeing some more comments. Yes, okay, perfect. So there we go. This is an overview of the contribution to solar system science of each of the Rubin bands. I and R are doing a huge amount of work. G and Z are also contributing a fair bit, and we can also see a bit about the average color from the offsets and the peaks of these. All right, we've got just a couple minutes left, so I'd just like to leave things off with one idea, and that's the SS object ID column. So all 4 of these solar system tables have a shared index, SS object ID. We can scroll back up here and see SS object ID in every one of these lists of columns. This is the Rubin 64-bit integer associated uniquely with every solar system object. And as I said at the beginning, we often care not just about a single piece of information of an object, but often we want a whole bunch of different information about that object. And that information is split up between these different tables because tables are generated the way the tables are generated. And so we need SS object ID to bring all this information together. And so let's investigate three famous objects. Bennu, this is a famous near-Earth asteroid. Eris is the largest trans-Neptunian object, largest solar system object that isn't a planet, largest dwarf planet. And then Hallman, which is named after the head of the Rubin Users Committee. Just a personal one. Okay, so we're gonna grab from NPC orb every row that has a name among these three names. We should expect three rows, one for each object, and we get out 3 rows. We are going to grab the SS object ID column out of that NPC orb result. So now we have the SS object IDs for these 3 objects, and we can query the other tables for them. And so now we can ask, for example, dia source, the dia source table for every dia source where SS object ID is one of these 3. So every dia source for those 3 objects, and in less than half a second, we get every first-year Rubin detection, those 3 objects. We included some truth columns in DB's 0.3, so you shouldn't expect name true to exist in dia source eventually, but for now, we can see that yep, these 3 objects are what we wanted, and I'll just leave things off with another nice plot we can make using the dia source information about these objects. So here's the main belt object. Its right ascension over time. We can see the squiggles. Oh, sorry, this is from the 10-year catalog. I'm realizing now. I said we would do everything out of the 1-year catalog, but this is 10-year NPC orb and 10-year dia source. Okay, so this is 10 years of right ascension and declination information. We can see these squiggles each year as the Earth moves, and then the larger sine wave as the object itself moves. And then we've got the sky path in right ascension versus declination. So we can see this main belt object makes a whole loop 360 degrees around solar system, or very nearly, in this 10 years, but it stays pretty tightly bound between declination of -20 and +20. So it's around the ecliptic the whole time. Meanwhile, the near Earth object, it has this crazy chaotic looking path that doesn't look whatsoever like a nice sky path. It also moves the whole right ascension, but ends up way further down to the south because NEOs are fast and crazy. And finally, the TNO, Eris, these are very slow and very well behaved. And so we see that the Earth's motion is actually a majority of the motion that we see of Eris over the course of this 10-year data set. It only moves about 2.5 degrees in right ascension and in declination over the course of the 10-year survey. So we can query object-specific information. We can learn about where these objects are over time. If you would like to hear more about this and do some more practice, either connecting these DP03 tables up to each other or to external services, please stop by the breakout room I'll be in the collaborative work time, and we can work through the rest of this notebook and talk more about the DP03 tables. But otherwise, I'm out of time. So thanks a whole bunch.
Thank you very much, Jake. That was really terrific. I learned a lot from this, after not being much of a solar system object astronomer. So that's great. Okay, at this point, we're going to take a short break. But while you are taking a break, what I would recommend that let us know whether you'd like to have a special breakout room that you'd like to attend or maybe even organize. I think, Jake, I hope that you would be able to do the solar system breakout room, which I will create while we're on a break. Is that right? Yeah, and I think that there was at least one breakout room that Douglas was planning to do. Was it about the tap service, Douglas? Is that right?
Yeah, I could do something on Top Cat.
Top Cat. Okay, that's right. It was Top Cat. Okay. And then I will stay in the main room in case if there are any questions or anything related to my presentation, or maybe anything more general. So let me just start working on those breakout rooms. Let me just, for the time being, I see we have, and then also there will be one more room where people who put their names, pictures, and information about their research onto the slide deck can go into that room, and maybe you can, one of us might be able to just walk through this, through those, so everybody would have maybe about a minute or two to advertise their own work and what they want to accomplish from the data previous on Rubin, or maybe in the future from Rubin itself. All right, so at this point, I am just trying to figure out who will be there. Let me see who else is of our team still on the call. So Jeff, would you be willing to go to the notebook aspect room? Is that acceptable for you? Let me just share my screen for this guy. And, we are right.
Sure, I'm available for any of the breakout rooms.
Okay, great. So I'm gonna put you into the notebook aspect, maybe because that's the one.
So were we gonna take a 5-minute break?
Yeah, we're essentially on break right now, so I'm just putting things together.
Okay, so we'll come back at 10:15.
10:15 would be good.
Just a few minutes, and then we'll start.
Yeah. Oh, you know, if people trickle in, that's fine. I'm gonna start setting up those breakout rooms with the and then I will set it up in such a way that people can choose their own room rather than I will pre-assign them to rooms. Okay. And I suspect at this point I will just stop the recording because I think we're not gonna record any breakout rooms or anything like this. So okay, stop recording.